In today's video, we're going over something called concavity. There's two types of concavity. There's concave up and concave down. Concave up just simply means as you go from left to right on a graph, it bends upwards. So that's going to look something kind of like this. As we go from left to right on the graph kind of bends upwards like this. It looks kind of like a U shape. And a simple way to remember that is just to remember concave up has this U in it, so that's what the graph's going to look like for a concave up. Concave down is just the opposite. As you move from left to right, the graph bends downwards. So that's going to look something like this. And as we see, as we move from left to right, the graph is going to be kind of an upside down U shape. It's going to bend downwards. And then a straight line would be considered neither concave up or concave down. And a vertical line is technically actually not even a function, so it would also be considered neither concave up or concave down. Okay, so now we have an understanding of concavity, but how does that relate to AI? Well, in the example of deep learning, there's a few things we have to review really quick before we get to that. The first thing is to remember that a neural network is just kind of a giant function. So as we've kind of gone over in some of the previous videos, but I'll quickly go over here again, in a neural network, you have an input that you're going to feed into the neural network, and this input goes to the first neuron, which has some sort of function inside of it. That neuron puts the input into the function and it spits the output to the next neurons, which kind of repeat the same process, pass it on to the next neuron, and this final neuron also has a function inside of it, which then takes those inputs and then spits out the final output in this simple example. So if you kind of nest all these, it's just kind of a giant function. And that means it's something that you can also graph. So an example could look something like this. You could have trained a neural network and you could feed, like the square footage of a house and kind of get the house price as the output. The second thing to remember is that these predictions that the neural network gives, like this line of predictions that the neural network is giving, this is based on two parameters that are inside each of these neurons, inside the function of each of these neurons. And those two parameters are W and B in this, again, this simple example. And we kind of talked about this in some of the previous videos. If it's still kind of hazy for you, that's totally okay. We're going to go into it with a lot more depth in future videos. The third thing to remember is that the way we adjust W and B to their ideal values so that this neural network is giving the best predictions it can is by using calculus. But how is that done? So say we're starting with a fresh neural network, so it's untrained and it maybe looks something like this with just, 4 neurons connected to each other. And again, each neuron internally has some function inside of it. In this example, we could just say they're linear functions, which look something like this. F of x is equal to wx plus b, for example, in this neuron. And this neuron might have something like f of x is equal to w4x plus b4. And the key point here is, again, that each neuron has a distinct function, a distinct set of parameters for each function. So w4 and b4 aren't necessarily equal to w and b, for example. Something else that we had just talked about is how neurons in actual neural networks have nonlinear functions inside of them. And that's something that is true, but again, in this simple example, just pretend that they're linear functions. Okay, so we have the parameters w and b, which are just sets of random values in this new neural network, which has not been trained. And the output of this neural network could look something kind of like this blue line, like we talked about. These are the predictions that the neural network makes for each square footage, the house price prediction. And when we want to try to train this neural network, what we can do is we can look at, okay, this is the predictions it's making right now. Let's compare those predictions to real world data, which here I have in red. So these red dots are just real world house prices. And what we can do is we can adjust W and B in each neuron by using these real house prices. So again, adjusting W and B in each neuron is going to change what this prediction function looks like. So how is this done? Well, one way to do it is to kind of measure how bad the neural network currently is at predicting things. This is something called cost. A way to do that is to take the distance of each of these points to the function. So this one might be kind of far, this one's pretty close, this one's a little, it's like in the middle, this one's pretty close, this one's pretty far, and we do that for every real data point and compare it to we find the distance it has from to the function, and we can add up those values. If that's still a little hazy for you, let's look at a more concrete example that hopefully helps. So say all of the parameters in this function are set to values like this. W1 is 1, W2 is 3, W3 is -5, W4 is 10, and B1 is maybe 10, B2 is 11, B3 is 0, B4 is -10. So say that we have randomly set the neural network to have these starting values as the parameters. So all these this W1 here is equal to 1, this B1 is equal to 10, and here W4 is equal to 10, and B4 is equal to -10. This is where when we create the fresh neural network, this is what the starting values are for all these parameters inside each neuron. And that's going to spit out a line, kind of like we talked about. It's going to have some sort of prediction if we graph the function of the entire neural network. And then we do what I just said. We say, okay, so how bad is the neural network right now at predicting things? And the way we can do that is by, again, just finding the distance between the real world data to the predictions the neural network makes, and we can add them up. So let's say in this example, for parameters of this, for all these parameters, the cost comes out to something like 72. So again, the cost is the distance from all these points to the predicted values of the neural network, and all of them added up. So let's say for all these parameters, it's just 72. And that can change. So if we change W1 to maybe 50 instead, that's going to impact what this function looks like, because this now becomes 50 times x plus whatever B1 is. So maybe it looks a little bit higher now or something. And that's also going to change the cost, because the distance from all the points to the predicted values that the neural network outputs is also going to change. So it could change to maybe something like 102. So what we just explained here is a very, very, very important concept in neural networks. It's something called a cost function. A cost function is a function in which you throw in all the parameters of a neural network. So that'll be like this W1, B1, all the way to W4, B4 in this example neural network. Basically, all of these parameters go into the cost function. And the output of the cost function is how bad the neural network is at predicting things. So that's just like kind of like this 102 we talked about. That's that distance we added up from all these points to the predicted values of the neural network. One thing I want to quickly note is that if a neural network has only linear functions inside of it, like we do in this simple example, it wouldn't actually have this sort of curved graph, kind of how we talked about in previous videos, but this is just some sort of example graph that I had here. It's not actually what this would look like. Okay, but how does all this relate to concavity? So say we have this extremely simplified neural network example where there's just an input and there's a very simple linear function inside the neuron, which, again, reminder, neurons don't actually have linear functions inside them. They have nonlinear functions. But just to make this simple, we're doing a super simple linear function inside this neuron. And the input gets plugged into this X, and this neural network just spits out an output. So what we can do is we can compute the cost for all possible W values. So what does that mean again? So if we remember, in this much more complex example, when you have a set of parameters, the neural network is going to spit out some sort of function, right? And for this set of parameters, it could look something like this. And when you change W, like we talked about, it could be maybe become slightly steeper, slightly straighter here, maybe just a little bit lower. It can just take on a lot of different shapes by changing these parameters here. So what we can do is for all parameters, we can find the cost. In this example, it's much more complex because there's 8 different parameters here. But in this example, we've simplified the neural network to just one to one parameter, just W. And what we can do is for every single possible W, we can find out how bad is the neural network at predicting things when W is equal to that value. So for W0, for example, the neural network might be give a cost of -1. When W equals 1, it might give a cost of 0. When W equals -1, it might give a cost of 0 again. And again, just to review, the cost is when you're comparing that actual real world data to the neural network's predictions, it's just the distance from those real data points to the predicted values, all added up for all these data points like we talked about. We add up that distance for all of them. And that kind of gives us an idea of how bad the neural network is at predicting things. So we do that in this simple example for every W value. And this graph here is going to end up being something that we had just talked about, the cost function, which again is the function that tells you how bad the neural network is at predicting things when you throw in all the parameters of the neural network into it. Now we finally get to why concavity is important for deep learning. So we often are going to want to pick a cost function that is concave up. So kind of like how we talked about right now in our naive cost function, we're finding the distance of all these points, and then we're just adding up that number, and then we're calling that our cost currently. There's a lot of other cost functions that we can select as well. So for one example might be you take all these distances and you square them. There's other options too, but basically you can select a cost function that always results in a concave up sort of function. That's not always possible, but it's just something you're going to see frequently. The whole goal of a neural network is to be as good as possible at predicting things, or as not bad as possible. And as not bad as possible means it has the lowest cost. The point at which it has the lowest cost is when it's best at predicting things. And for concave up cost functions, that's really easy to find because it's just going to be at the bottom of this U shape. And in this case, that happens at when W equals 0. So that is when the neural network is, this very simple neural network is at its best at predicting things based on the real data points that we kind of use to calibrate W. So this might have all been kind of a lot, but that's completely okay. We're going to cover all these concepts in a lot more depth, but it's just good to kind of get kind of a broad overview of them. But the main takeaway from the video today should be you should be able to identify if functions are concave up or concave down or neither based on their graph.